Alright guys, so in this video we are starting to look into anti-differentiation by substitution. So we're going to start evaluating integrals, specifically indefinite integrals, by substitution. So that's an overall goal that we have for this lesson. Now, this video specifically is going to dive into some properties and some rules for basic integration, and then we are going to look into a few examples for each of the basic properties. And then in the next following video, as we kind of get a little more comfortable just taking some more basic integrals for indefinite integrals, we are going to look into how to evaluate an indefinite integral by using substitution specifically. So let's take a look here first and foremost of what is the definition of, and I'll come back here to the properties in just a sec. What is the definition of an indefinite integral? The family of all antiderivatives of a function f of x is the indefinite integral of f, so the function f, with respect to x. We talked about that a lot, with respect to a certain independent variable, and is denoted by the following. And so we've seen this before. This is not anything new. Our integral sign of f of x dx. The only thing that we should be noticing here is that we do not have the upper and the lower limits. So this right here, ladies and gentlemen, is the indefinite integral. No upper, no lower limits. Okay? It is also true that if capital F, if capital F is any function such that the derivative of capital F, remember capital F is really our antiderivative, right? So the antiderivative, its derivative equals F. Let me say that one more time. Think about it. The antiderivative of a function, we're going to call that capital F, its derivative is that function. That only makes sense, right? Then we can say that it has this particular denotation, right? So this is what this would look like, guys. It's the same thing as in saying then the integral of f of x dx is equal to f capital of x plus c. So it's just that we've been doing in the past, taking the antiderivative of the function, which is denoted by capital F, and then because it's indefinite, we have the constant of integration c. Alright, so now let's scroll back on up, and as we're going through some of these, you might want to pause the video, and I think it'd be good to maybe have a little note card to kind of keep all of these properties and formulas for integration on there. So a couple of the ones we're not going to talk about too much. We've talked about the indefinite integral properties using a constant being multiplied by the function. We can pull that on the outside of the integral. We have discussed the addition and subtraction properties for using integrals. We've talked about our power formulas as well. We're going to do one quick one with the power formulas. So let's start basic. Let's just say I wanted to evaluate the integral of 5x to the fourth dx. So going by our power formulas, n in this case, n is 4. So you will raise the power and divide by that new power that you just raised it to. Well, if I raise 4 by 1, that is 5, and I also will divide by 5. So this really is 5x to the fifth divided by 5, but they cancel on out. So in the end, it's just x to the fifth plus c. So that's how our power formula looks. To the right of that, you see, don't forget the derivative of the natural log is equal to 1 over u. So that means the antiderivative of 1 over u is the natural log. Also, as we scroll down here, you can see some trig formulas just to kind of always keep in mind of what is true about our trig formulas and knowing what the derivative was and then the antiderivative will be. And then we also have our exponentials that go along with it as well. So we know the derivative of e to the x is simply going to be e to the x, so that means the antiderivative would also be e to the x, okay? And again, we're not talking about different things other than just simply x or u in this case. All right, so we'll get there though when it comes down to substitution here in just a bit. But I want to take a look at the one all the way to the right, a to the u du. All right. So let's say, for instance, we have the integral of 5x ln of 5 dx. All right, so let's take a look here first and foremost. A to the u will be represented by the term 5x. ln of 5, that is just value. That is a numerical value. That is a constant that I can bring on the outside. And so now, going by our rule of thumb in here, this would be a to the u, alright, a to the u, which is 5x, divided by the natural log of a, which is 5. But don't forget, when you're evaluating, you had the ln of 5 on the outside. That will cancel and that will cancel, and so you're left with just 5x plus c. Okay? So a very brief introductory video, just getting us warmed up with some of these formulas and defining the indefinite integral. In our next video, we're going to start diving into using substitution as a way to evaluate indefinite integrals.